For centuries, the world adhered to the geometric principles laid out by the Greek mathematician Euclid. His treatise Elements became the bedrock of geometry, shaping our understanding of lines, angles, and shapes.
At the heart of this Euclidean world lay 5 fundamental postulates, self-evident truths upon which the entire system was built. The 5th postulate, however, stood out for its complexity.
It stated that if a straight line falling on 2 other straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which the angles are less than 2 right angles.
In simpler terms, it established the concept of parallel lines in a plane that never intersect, no matter how far they extend. This seemingly straightforward statement, however, became the subject of intense scrutiny and debate for over 2 millennia.
Mathematicians were troubled by its complexity compared to the other postulates, which were simpler and more intuitive. Could this fundamental tenet about parallel lines be proven from the other 4 postulates, or was it an independent truth in itself?
The quest to resolve this question would lead to one of the most profound revolutions in the history of mathematics. Euclid's parallel postulate, despite its cumbersome wording, was essential for the development of Euclidean geometry.
It underpinned countless theorems and proofs, forming the very foundation of our geometric intuition. From the angles of a triangle adding up to 180 degrees to the Pythagorean theorem, this postulate was an invisible hand guiding our understanding of the world around us.
It was a cornerstone of a system that seemed to perfectly describe the physical space we inhabited. However, the seeds of doubt had been sown. The very existence of this seemingly complex postulate, intertwined with the elegance and simplicity of the other 4, hinted at a deeper truth waiting to be unearthed.
Could our understanding of space, so confidently described by Euclid, be incomplete?
The quest to prove the parallel postulate would not only challenge the foundations of Euclidean geometry, but also pave the way for new, unimaginable geometries that would reshape our understanding of the cosmos. The history of mathematics is replete with attempts to prove Euclid's 5th postulate from the other 4, a testament to its enduring enigma. For centuries, mathematicians grappled with this challenge, seeking to solidify the foundations of Euclidean geometry. Some of the most brilliant minds in history, from ancient Greek mathematicians to Islamic scholars of the Golden Age, dedicated themselves to unraveling the mystery of the parallel postulate. One approach involved trying to find a contradiction that would arise if the parallel postulate were false. If the denial of the postulate led to absurd conclusions, it would indirectly prove the postulate's validity. This method, known as proof by contradiction, seemed promising, but every attempt to corner the postulate into a logical inconsistency failed. The elusive proof remained just out of reach. Another strategy involved replacing the parallel postulate with an equivalent statement, one that could be more easily derived from the other postulates. Mathematicians explored numerous alternative axioms, hoping to find one that would seamlessly integrate into the Euclidean framework. Yet every substitution they proposed, while seemingly plausible, ultimately led to geometries that deviated from the familiar rules of Euclid, hinting at a realm beyond the Euclidean horizon. These persistent efforts, though ultimately unsuccessful in proving the parallel postulate, were far from futile. The struggle to pin down this elusive truth forced mathematicians to scrutinize the very foundations of geometry, pushing the boundaries of their understanding. It led to the development of new geometric concepts and techniques, enriching the mathematical landscape. The quest to prove the 5th postulate, though initially aimed at reinforcing the Euclidean edifice, would inadvertently lay the groundwork for its eventual transcendence. The 19th century witnessed a seismic shift in the world of mathematics. The long-held belief in the absolute truth of Euclidean geometry, a system seemingly unshakable for over 2 millennia, was about to be challenged. The catalyst for this revolution was the audacious idea that Euclid's parallel postulate might not be a universal truth, but rather one possibility in a wider geometric landscape. This radical notion, initially met with resistance and skepticism, emerged from the tireless efforts to prove the parallel postulate.
The repeated failures to force the 5th postulate into the Euclidean framework, coupled with the emergence of alternative geometries, led some mathematicians to a startling realization. What if the parallel postulate was not provable because it wasn't an inherent truth but rather a choice, a specific constraint that shaped a particular type of geometry?
This paradigm shift gave birth to non-Euclidean geometries, mathematical systems that dared to explore the consequences of denying Euclid's fifth postulate. These new geometries, far from being mere intellectual curiosities, offered a glimpse into a world where parallel lines could behave differently, where the angles of a triangle might not add up to 180 degrees, and where the curvature of space itself played a fundamental role.
This was a radical departure from the flat Euclidean world that had dominated mathematical thought for centuries. The development of non-Euclidean geometries was not merely a mathematical curiosity, it was a profound philosophical shift.
It challenged the very notion of absolute truth in mathematics, suggesting that there could be multiple, equally valid geometries, each with its own set of axioms and implications. This revolutionized the way mathematicians viewed their discipline, opening up new avenues of exploration and fundamentally altering our understanding of space and geometry.